kind of important to record the review session. I think I got it figured out. Okay, so let's see here. That's good, good. All right. First thing I want to do is, well, unhide the solutions. Oops. So I typed up the practice test solutions. I've still got 2 copies of the practice test. If you didn't get a copy, does everyone have a copy? Take a copy, take a copy. Okay. So I just want to show you guys a couple of things here on Moodle because I put up a ton of different stuff yesterday. Not a ton, but first of all, I posted the assignment 5, the short solution. So assignment 5 is due on Monday, right? That's the same day as the test. In case that's news, we've got a test on Monday. And so what I did, because I know it's really hard to go through the test and kind of not know where you're at. And so I posted these kind of short solutions, right? So for 1A, you're doing a confidence interval. So I just gave you the confidence interval that you should get, right? It's still your job to interpret the interval, show the work for getting there, right? But at least you have these little check-in points. Part B is a hypothesis test, right? So I give you the t that you should have calculated to 3 decimal places and also what the conclusion is, right? So here we do not have enough evidence to reject H naught. Of course, you have to do everything around it, right? But at least now you kind of have these kind of check-in points of where it should be at. So those are posted on Moodle, so you can have a look through there. And in case you haven't had a look at the assignment 5 extra practice problems, there's also the solutions. The extra practice problems are just a series of, I think, 10 questions that I've typed up, just so you can get practice in reading these questions and figuring out what type of question is this, right? Because what you've probably noticed is reading the question and trying to figure out what type of question it is can be really tricky, right? And so I want to give you guys practice, and I posted the solutions for what type it is, and I've tried to kind of explain why that is. Sometimes it's just because we have 2 independent groups, right? And there's 2 sample means. Also, on your formula sheet, right, the types of problems that you have are just the names of the sections, right, on the left or on the right-hand side. Right, so the types of questions that we can have on this test is 1 sample means sigma known, 1 sample means sigma unknown, paired data or matched pairs, and then 2 sample means, which is the 2 independent samples that we talked about last day. Right, and so they're on here. And so once you've read a question and you've decided, okay, this is the type of question that I have, then you can just kind of zero in on that section of the formula sheet and forget about everything else. Right? And so it's going to be important that you are able to read these, figure out what type of question you have, right, and get really good at doing that, especially because you'll have to do that on the final as well. Right? So, what else did I do on here? Posted those solutions. Oh, and I also want to show you, I had a little mistake on assignment 4. It was not a big deal when you guys were doing it because you'd only seen 1 type of question. You'd only seen one sample means sigma known, but the way the question was worded on the one that you did, it was actually a sigma unknown problem, right? Because the standard deviation came from the sample. And so just I've highlighted what it should have been to be a sigma known type of problem, right? So it would have said, assume the standard deviation of all house prices is 94,300, right? So that's the change. Nothing in your calculations changed or anything like that, but just as a heads up, go back and check those revisions. And I've posted the solutions as well. Okay. What else did I do on here? Oh, and of course, there's the chapter 5. I don't know. I moved these around so they were in order, but then they got jumbled again somehow. But there's chapter 5 practice problems here with solutions typed up, right? So you can always go through and do those as well. And then you have the full solutions for even more practice. Okay. And the solutions that we're about to go through, I've posted here. Okay. But also pulled them in here. Any questions before we start? No. So because of the setup of the test, right, I had to give you practice problems for all the different types. Okay. And I know it's a little bit tricky, but I find, so I've done this before where I just give you questions to choose from and you just pick which ones you want to do. I find that it's really interesting to see what questions people want to do. Right? And also it gives you a choice, right? So you should feel confident that you can do well on this test, because as long as you're comfortable doing 2 of these 4 types of questions, then you just pick those, tell me the type of the other 2, and then we should do well. Okay. When am I here? I'll be here tomorrow, Friday, Saturday, Sunday, because I'm in town. So if I'm not in Ottawa, then I'm usually here on the weekends. I know. Get a life. No, I just love working so much. And I also don't have a life, so. Anyways, I'll make a note of that though here, because I know you're probably not studying for this until probably the weekend. That's fine. So I'll be around here if you're studying here, or even if you text me or email me, then I'm around. Okay. So, I will be at school. I know it's tricky. I didn't print off these solutions because I know you guys had various amounts of work done on it already, so didn't really see a point. But I will be at school Thursday, Friday, Saturday, and Sunday. Stop by anytime. My office is C104, in case you don't know. Or text with questions. At this point, it's probably easier to text just because you're probably working on a problem. You can just send me a picture and then I can answer it and send you a picture back. Like permanent Snapchat. My number is 250-864-8386. So I'm around. If you have any questions, even if it's really late on Sunday, you can still give it a go. So remember the layout we said for this test was, okay, there's a question like question 1 on the practice test. That one has to be there. Okay, so here, this is on the test. Not this exact question, right, but this type of question. And then for questions 2, 3, 4, 5, right, you're gonna pick 2 of the 4 that you're gonna do and then tell me the type of the other 2. Okay? So above question 2, I'm just going to say, pick 2 of the following 4 questions to do. Tell me the type of the remaining 2 questions. Yeah. It's, well, it'll have 5, just like the practice test, but you only have to do question 1 and then 2 of the, yeah, question 1 and then 2 hypothesis testing questions, 2 confidence intervals, right? 1 for each question that you do. And then tell me the type for the other 2. So just say if it's 1 sample mean sigma known, 1 sample mean sigma unknown, matched pairs, or 2 sample means. Yeah. Let me see here. Question 1 is going to be out of 10-ish. And then the remaining, so the long answers will be about 10 or 11 because I'm doing a mark for the type. And then 10, 11, 22, 34-ish. So I know that's not a ton of marks, which is kind of high pressure, right? But as long as you follow the steps and everything, you'll be fine. Okay. Any other questions? I know it's kind of a weird layout, so yeah. No multiple choice. I know, right? I know, multiple choice is tricky. It's tricky. So it's all written. You can kind of BS your way through it. No, not really. So, any other questions? No? So because I've typed up the solutions, then we'll just kind of talk about these. I'll highlight some things to keep in mind, right? And then we'll kind of go from there, right? But if you came across a question as you were working on these, then absolutely bring it up. So for the first question, it's going to be one of those from assignment 4 in chapter 4, where we have something follows a normal distribution, right, with a mean this and a standard deviation this, and then we have to use z-scores to find probabilities. Or in this case, I gave you the probability of the area under the curve, and you have to find the cutoff, right, curveball. But either way, right, how it's going to go is part A is going to be for a single observation, which is actually from chapter 3. Part B, I tell you, okay, now you collect a sample of this size. What's the sampling distribution of X bar? And then part C, use the sampling distribution of X bar to find some probability associated with the mean observation. So they'll have the same type of layout. So we want to know how slow does the slowest 45% of West Indian manatees travel. And so what we have, if we sketched it out, it would be something like this. Right? We've got a normal distribution because the speeds are normally distributed with a mean of 3.8 and a standard deviation of 1.34. At some unknown point here, below this point, we've got the slowest 45% of manatees. Right, so this is one of those where I give you the area under the curve and you have to find the cutoff. Right? I could give you some value. Right? What's the probability that a manatee is slower than 2 miles per hour, for example? Right? Those are all fair game. And so now, what we have to do is we have to find the z-score that corresponds to an area to the left of 0.45. And so here, I've written out, okay, using the z-table, we find the table entry closest to 0.45. So if you go to your table, your Z table. We know we're on the negative side of Z just because the area to the left is less than 0.5, right? You have to cross the mean to have an area greater than 0.5. So we know we're on the left-hand side. And we're just gonna peruse the table. Somewhere down here, we've got choices between 0.4522 and 0.4483. Quick calculation on your calculator, you'll find that 0.4483 is a little bit closer to 0.45. So that's the one that you're going to use, which corresponds to, so now you can figure out, okay, well, that corresponds to a Z of negative 0.13. Okay. So that's how you're going to work backwards. So I've got that in the solutions here. And so, which corresponds to Z equal to negative 0.13. Now we can use this value of Z to solve for X. And so, done the rearranging here, and with rounding, we find that X is 3.63. If it's important, I'll tell you how many decimal places to give your answer to, right? Otherwise, just do 2 or 3, right, if I don't specify. But if it's important, I'll tell you. So the slowest 45% of manatees travel at speeds up to 3.63 miles per hour. That's that question done. You don't have to, like here I've got the graph typed up. You don't have to include the graph, but usually if you've got the wrong idea about the question, right? If you've misinterpreted the question, but you communicate how you interpreted the question in the graph, I can give you more marks just for being consistent, right? So here you're saying, well, this is how I understood the problem. And then I can be kind of more lenient. As long as you follow through, right, then that's better than just saying, oh, here's what I get. So you don't have to include the graphs, but they will help. Any questions about that one? So that was kind of a throwback to chapter 3, and then the rest are from 4 and 5. So part B, now you sample 50 West Indian manatees. What's the sampling distribution of their average speed, X bar? So X bar follows a normal distribution with a mean mu and a standard deviation sigma over root n. We did this on assignment 4, right? Actually, we did this entire question-ish on assignment 4. And so I would actually just stop here. I wouldn't go through and calculate 1.34 over the square root of 50 because I'm lazy. I would just leave it as that. And so what I'm going to do here is I'm just going to say that this part is optional. Part of this too is, I know it's really hard to know, like, what do you have to show, what do you not have to show. So as we go through this, I'll try to highlight anything that's kind of optional, right? Me showing extra work just in case you're referring to it on your own and you're trying to figure it out, right? But either of those answers are good. Okay. So that's the sampling distribution of the mean. Part C, what's the probability that the mean speed, right, now we're talking about the mean, which means we have to use the sampling distribution of the mean, right, of your sample is less than 3.4 miles per hour. So now we've got a mean speed of 3.4. It's still centered on 3.8, but the standard deviation is not 1.34 as it was for a single manatee. Now it's for the mean of a sample size of 50. And so we find a Z of negative 2.11. Z scores, we round to 2 decimal places to match the Z table. T scores, we round to 3 decimal places to match the T table, right? Or at least 3 decimal places. Okay. So what we can say is that using the Z table, we find the area to the left of Z equal to negative 2.11 is 0.0174. That is the area that we want, right? And so we're done. If we wanted to know what's the probability that the mean speed is more than 3.4, then we would want the area to the right. Therefore, the probability that the mean speed of your sample is less than 3.4 miles per hour is 0.0174. Done. So there's definitely one of those types of questions, same parts A, B, C, right, but just about something else. Any questions? Okay. So, yeah, I'm so curious to know which types of questions you decide that you feel the most comfortable doing. Okay. For now, we'll just work through all these. You've probably noticed if you went through it as you were reading them, right, they're actually just in the order on the formula sheet. Right? I did that on purpose because, at least the way my mind works, if I'm in a test, I'm trying to remember what the practice test was like and trying to kind of make connections between the two, right? And so at least if the practice test is in the same order here, even if they're, because they will be jumbled on the test, right? Then you can say, oh, that was like question 3 on there. And then you can just kind of link it to the formula sheet, right? So there's a method to my madness there. I don't know if it's going to help you, but better than mumbo jumbled. Okay. But like I said, there's also those assignment 5 extra practice problems where they are just in random order, where you can practice reading them just in different orders and trying to figure out what type they are. Okay. So question 2, you took a random sample of 48 Amazonian manatees and found their mean speed to be 4.4 miles per hour. So this is your sample mean. So you have one sample of Amazonian manatees and you have their sample mean. Assume it is known that the standard deviation of speeds for all manatees, that's the population, is 1.34 miles per hour. So this is going to be, as far as the type goes, this is going to be a one sample means problem with sigma known, right? Just because I'm saying, okay, assume that we know the standard deviation for all manatees. That's the population of manatees. And so here, all manatees is the population, which means that what I'm saying is that sigma is 1.34. I've also got it explained, right? One sample means sigma known, since we're assuming we know the standard deviation for the population, which is all manatees. Right? So the question for these first 2 types, right? Sigma known, sigma unknown, it's not whether we know the standard deviation or not, right? It's going to be, where did the standard deviation come from? Right? So we'll always have a standard deviation, but the question is going to be, where did the standard deviation come from? If it came from the population, sigma is the population standard deviation, right? So then sigma is known. If in the question, when you're reading it, and it kind of implies that, okay, you collected a sample and you found the mean to be this and the standard deviation to be this, that's implying, bless you, that you have the sample standard deviation, right? So then you have sigma unknown. Part A. Is there evidence that Amazonian manatees are significantly faster than West Indian manatees? And this is referring to the previous question, so I've just got to recall that West Indian manatees travel at a speed that's approximately normally distributed with a mean of 3.8 and a standard deviation. Of course, we're saying that's the standard deviation of the speeds for all manatees. So it will be the same, 1.3 miles per hour. So what do we want to do here, right? We've got a sample mean of 4.4 that we want to compare to, we want to see if that's significantly faster than 3.8. Right? Because that would show that Amazonian manatees are significantly faster than West Indian manatees. So as far as our hypothesis goes, the value that we want to compare our mean to, our sample mean to, is going to be this 3.8. And so we've got H naught is that mu equals 3.8. And so what I want to do here, 3.8 miles per hour, this is the value we want to compare X bar to. Right? And that's the value that's going to be your mu sub 0 or your mu naught. Okay? Whatever value you want to compare the sample mean to, that's your mu naught. If you're looking at the formula sheet, right, I've got the hypotheses laid out for you, but for one sample problems, right, both of them look the same, but for one sample problems, you have to identify what value do you want to compare the sample mean to, right? That's going to be your mu naught. Okay? Whereas for matched pairs and for two sample means, the null and alternative hypotheses, they're predetermined, right? They're fixed. They're not going to change from what's on your formula sheet. So that's why I like them better. A little bit more work, but easier in the long run. And we want to show that Amazonian manatees are faster than 3.8. And so because I only care about one extreme, right, this is where we figure out if we have a one-sided or a two-sided test for the p-value, right? So if I only care about one side, then this is a one-sided test. Once you have figured out what type of question you have, figured out what your null and alternative hypotheses are, everything's kind of smooth sailing from there, right? Because then you do the test, so you do the calculation that follows the null and alternative hypotheses on your formula sheet, right? So in this case, we're going to calculate a z-score. And then because we've got a z, we have to use the z table to find the p-value. And so we find a z of 3.10, right, rounding to 2 decimal places. Yeah. So here, because I'm saying, so you took a random sample of 48 Amazonian manatees and found their mean speed to be 4.4, right? So what I'm saying is, okay, you collected a sample and then you calculated the mean of that sample, which is X bar, right, the sample mean. And so it'll usually be laid out something like this, right? You collect a sample and you found the mean to be this, compare it to this value. Okay. So I know it's tricky. Just got to read a lot of problems, try to figure it out. Any other questions about that one? Because I know it's tricky. Okay. So once you have your z-score, you can draw out your curve if you want, and remember the p-value is the probability of seeing something as extreme or more extreme than what you saw, which puts you in the tails, right? In this case, we only care about one tail. So this area here, even though you can't really see it, or you really can't see it, is your, oh, that got ugly. This here is your one-sided p-value. You know how to use z-scores to find areas under the curve, right? And so you know how to use a z-score of 3.1 to find the area to the right. So we say using the Z table, we find the area to the left of Z equal to 3.1, right? Because the table always gives you the area to the left. In this case, we want the area to the right, so we have to take it an extra step further. So the area to the left is 0.9990. So the area to the right is 1 minus that. So we have an area of 0.0010. Therefore, the one-sided p-value is 0.001. I actually don't. Once you get used to t-tests, right, which is one sample means sigma unknown, matched pairs, it's for two sample means, right? I actually prefer to stick with those once you're used to working with those, because the Z-scores, that was a long time ago, right? But again, up to you. If you like to work with Z-scores, take that question. So our conclusion, if the P is low, the null hypothesis must go, right? And so if the p-value is less than the alpha level, we can reject the null hypothesis. So in this case, since our p-value of 0.001 is less than our assumed alpha level, because I didn't give you one to use, of 0.05, we have enough evidence to reject H0 in favor of HA. And then you don't want to forget, what does that mean in terms of the question? Well, therefore there is evidence, and you just reword the question as an answer. Is there evidence? Yes, therefore there is evidence that Amazonian manatees are significantly faster than West Indian manatees. Okay. Any questions about that hypothesis test? Yeah.
How many points are given to just the conclusion?
3 marks. So 3 out of 7 marks typically are for the conclusion. So 1 mark, 2 marks, 3 marks. So the conclusion is kind of the moneymaker. So you want to make sure that you get that right. Okay. Let's do the confidence interval. So construct a 95% confidence interval for the mean speed of Amazonian manatees. Does this interval confirm your findings in part A? So again, because you've already decided that this is a one sample mean sigma known question, that's not going to change from part A to part B, right? That's going to stay the same. So you already know how your confidence interval is going to be set up. Right, so you can start and you can write out the formula that you have to use, right? X bar plus minus Z star times sigma over root n. We have X bar from the question, right, 4.4. And then we have sigma 1.34 and we have n, what was it, 48? Yeah. We just have to find Z star. Remember how we find Z star? We use the T table is the easiest way. You could use a Z table, but it's a lot more work, right? And so we said, okay, we're going to use a T table with a confidence level of 95%, and then we roll down to the very bottom, or almost bottom, to this Z star line. So we've got Z star is 1.96 for a 95% confidence interval. Just a stretch arm? Yeah. So here I've got a note, using the T table, we find Z star is 1.96 for a 95% confidence level. You can plug in, so what you have to show in terms of work is show the empty shell of the formula, right? Just to show off to me that you know which one to use. Plug in the values, show the margin of error, and then if you wanted to skip straight to the rounded values, that's fine. Okay. So I'm going to make a note here that this kind of midpoint here is optional. Everything else I want to see, right? I want to see, do you know which formula you're supposed to be using? Do you know which values go where? And then show me what you found as your margin of error, just so I can check in and see that it's right. And then give me the interval. Whenever you make a confidence interval, right, we have to interpret that interval. And so we use the same blurb over and over again, right? We're 95% confident that the interval from 4.02 to 4.78 captures, and then whatever I asked you to make an interval of, right? The true mean speed of Amazonian manatees. Here, there was a little follow-up part, right? Does this, what was it? Does this confirm your findings in part A? This interval, so in part A, we said that yes, mu is larger, significantly larger than 3.8. Here, this whole interval, right, all of it is consistently over 3.8, right? In terms of a number line, 3.8 would be over here. And so because this is consistently above or larger than 3.8, it does confirm the findings from part A. And so I've got that here. Since this interval is consistently above 3.8, it confirms our findings from part A that Amazonian manatees are significantly faster than West Indian manatees. Okay. Any questions about that one? Even though it might not feel like it right this very moment, by the end of this course, you will be hypothesis testing and confidence intervals, just champs. Okay, so you will be doing so many of them that they'll just kind of become, okay, fine, another confidence interval, another hypothesis test, right? I know that it's all new and this is the first time we're being tested on it, but it's going to be a-okay. Any questions about question 2 before we go to question 3? Question 3. An insurance company is reviewing its current policy rates. When originally setting the rates, they believed that the average claim amount was $1,800. They are concerned that the true mean is actually higher than this because they could potentially lose a lot of money. Sounds reasonable. They randomly select 40 claims and calculate a sample mean. So here's your sample mean of 1950 with a standard deviation of 500. Because of the way this sentence is set up, right? So you've randomly selected a sample of 40 claims and you found the mean to be this and the standard deviation to be this. The standard deviation here is from the sample, right? This is your sample standard deviation, which means S is 500, which means sigma is unknown because you only know the sample standard deviation.
So then if it was, if sigma was known, you would have something with the population or all?
Yeah, yeah. I would have to say, assume it is, usually I start with assume. Assume it is known that the standard deviation for all claims is 500. Right. Yeah. Whereas here, it's from the sample, so it's going to be a little bit different, right? We can also highlight that this 1950, that's your sample mean, so X bar is 1950. So we've collected one sample, and sigma is unknown, right, because we've got the standard deviation just from the sample. And so we've got one sample mean, sigma unknown type of problem. Part A is a little cryptic, right? But if you think about it, we can figure this out. So should the insurance company be concerned Remember, so they assumed that the mean claim amount was 1,800. They're only concerned if the mean claim amount is actually more than 1,800. And so really what this is asking is the mean claim amount higher than 1,800? So sometimes we have to read the question and just kind of map it back to the information that we were given earlier and just say, okay, well, what does it mean if they're concerned? Right. So in terms of our null and alternative hypothesis, right, we're comparing our sample mean of 1950 to 1,800. And so if they're not concerned, right, then mu is just 1,800, right? Not significantly different from 1,800. 1950 is higher than 1,800. We want to know if it's significantly higher than that. Right? And so the alternative hypothesis, this is where they should start being concerned. If we end up rejecting the null hypothesis in favor of the alternative, then they have to kind of go back and change their insurance rates and all that kind of stuff. Okay. And so here, if we go with the null hypothesis, then there's no concern, right? Because then it's just business as usual, everything's the same. And then if we reject the null hypothesis in favor of the alternative hypothesis, then they should be concerned. Bless you. Because I only care about one extreme, right? Are the mean claim amounts higher than 1,800? This is a one-sided test. Right. So the one-sided test is coming from the alternative hypothesis, right? It doesn't come into play until step 3 where we have to find the p-value, right? But I know that's kind of a hard part of this problem, or these problems, I should say. Okay. Once we've got the type figured out, the null and alternative hypotheses set out, then we just keep going on our formula sheet, right? So we're in this one sample mean sigma unknown section, right? After the null and alternative hypotheses, you've got a t that you have to calculate, and so that's the next step that you have to do here. So we calculate t, and we find a t of 1.897. That's big, right? It's getting close to 2, which in our minds is kind of this threshold where we're probably going to start rejecting the null hypothesis. And so the idea is, if we've moved out far enough into the tails on either end, then we're going to reject the null hypothesis. Here it's kind of borderline, right? 1.897. So we're going to find the p-value just to see if we can reject the null hypothesis or not. Notice that I gave you an alpha level for this one. So use a hypothesis test with an alpha level of 0.01, so not 0.05 this time, but 0.01. So this area here is going to be our one-sided p-value. The t-table just gives us the one-sided and the two-sided p-values, so we don't have to think about it so much, but it's there and it's kind of underlying. To find the p-value, we say, okay, using the t-table, because that's what we have to use, we calculated a t, so we have to use the t-table. So using the t-table, and in using the t-table, we have to know our degrees of freedom. With degrees of freedom equal to n minus 1, which is 40 minus 1, which is 39, right? If you go to the table and you try to find 39 degrees of freedom, you're caught choosing between 30 and 40, right? And so you have to show off that you know to go down to 30, right? Even though you're closer to 40, you can't round up because you don't have that big of a sample size, right? So we always have to go step down one. Unless your degrees, so say you got 19 degrees of freedom, there is a 19 line here, then you can just stay there. So we find, oh, I can stay there. 1.897, was that what the T was? Yeah. So we're going to be using 30 degrees of freedom. So you take your T that you calculated, 1.897, and you just try to figure out where it's going to go on this line. 1.897 is somewhere between 1.697 and 2.042. So you jot those down. In this short little blurb, you're showing off 3 things that you know, right? You're telling me, okay, I calculated a T, so I know I have to go to the T table. You're showing me, I know I have to calculate the degrees of freedom, and I know how to do that, so I guess 4 things. And also, you're showing off that, okay, I didn't find 39 in the table, and so I'm using 30. Okay. So you're showing off a lot of things that you know and that you're using, so you may as well write them down so that you're telling me all the things that you know. Okay. And then when you're writing this out, how I just start it, even before I've gone to the table and found these values, I write out my calculated T in the middle, right? Absolute value brackets around it. And then I do my less than signs. And then I can do my, I know I need to find a one-sided p-value. So I can write that in the middle as well. Also surrounded by less than signs, because I don't like to think about inequalities. So for me, if I'm always using this one, right, they all look the same, then I don't have to think about it so much. These ones will just be in the order that they show up on the table, right? The only switcheroo that we have to make is when we go to the one-sided p-value, we have to read them from right to left, right? And so we've got our T that we calculated, it falls somewhere between here and here, and we need to find the one-sided p-value, which is the top one, and we read them from right to left, so it's between 0.025 and 0.05. So those you switch around, everything else just kind of flows. So now we have a range for our one-sided p-value, and so we know it's somewhere between 0.025 and 0.05. Since our one-sided p-value, so now we can do our conclusion, right? Since our one-sided p-value is somewhere between 0.025 and 0.05, it's not less than our alpha level of 0.01. Right? And that's why it's important you use the one that I gave you, because it would be less than 0.05, but it's not less than 0.01. Right? Which means we do not have enough evidence to reject H naught. Okay? So what we're doing when we're using an alpha that's smaller, right, we're making it harder to reject the null hypothesis because we have to move further out into the tail than we normally would, right? And so one reason that the insurance company might use a smaller alpha like 0.01 is because it would be a lot of work to go through and change the rates, so they want to be really sure that they have to, right, in this case. But anyways, if we're not rejecting the null hypothesis, that means that the mean claim amount is not significantly higher than 1,800, so the insurance company does not need to be concerned. Okay. Any questions about that one? Okay. So now we can answer this question again using a confidence interval instead. Okay. So use a 90, so should the insurance company be concerned? Use a 98% confidence interval to test the hypothesis. Okay, fine. Again, you've already decided what type of question this is, And so the confidence interval, the formula for the confidence interval is just in that same section. And so, of course, you know X bar from the question, you know S and you know N. You just have to find T star. T star we find basically the same way as Z star. It's just we have to go until we hit our degrees of freedom line. And then we stop there instead of going all the way down to Z star. Okay. So again, you're going to show off, okay, I have to use the T table with, and here, because you already showed all your work for finding your degrees of freedom in part A, you don't have to show it in part B, but it's really not that much work, so why not? You could say, using the T table with degrees of freedom equal to 30, right, just because you've already shown me, and a confidence level of 98%, we find T stars 2.457, right? Because we went here and we found 98% confidence level and we had 30 degrees of freedom. It's down here at 2.457. So that's how you're going to find your T star. I want to see, again, I want to see the empty formula. I want to see all the values plugged in, and I want to see the margin of error. This one is optional, but then I want to see the rounded one at least. So this one is optional. Everything else you have to show. Our interval is from 1755 to 2144. Just looking at this, 1800 is in there somewhere, right? Just kind of on the cusp here, right? But it's still in the interval. And so that's the same as not rejecting the null hypothesis, right? If 1800 is in the interval, then we're 98% confident that this interval from 1755 to 2144 captures the true mean claim amount. Because 1800 is in this interval, then there's no reason to think that it's any higher than 1800 yet. Oh, so here, so it's plus and minus, right? So you want to do 1950 minus 194 point whatever, and that's this value. And then you got 1950 plus 194, and that's this value. Right, so it's just like, you know, it's 2 degrees out plus or minus 3 degrees. Huge margin of error. Giving myself some wiggle room. Right? So same idea, right? Because you get a lower bound and an upper bound. So again, the insurance company does not need to be concerned because 18 is inside this interval, and so we feel pretty good about saying, no, the rates are not significantly higher, or the claim amounts are not significantly higher. Any questions about that one? No? Question 4 then. Alternative sources of energy are of increasing interest throughout the energy industry, of course. Wind energy has great potential, but appropriate sites must be found for the turbines. To select the site for an electricity generating wind turbine, wind speeds are recorded at several potential sites every 6 hours for a year. 2 sites not far from each other looked good. Woohoo. Each had a mean wind speed high enough to qualify, but we should choose the site with a higher average daily wind speed, of course, right? And so this one's a little bit sneaky, right? Because we know that matched pairs is when we've got 2 observations on the same subject, right? Here, we kind of have to shift our thinking a little bit because we've got 2 observations at the same time point, right? So the turbines or the locations aren't the subjects, right? We're talking about, okay, the wind speed here and the wind speed here. The reason we want to treat these as paired data is because what if it was a really windy day, right? Then if we're treating them as pairs, then we can capture the difference between the two, right? On a really windy day, on a not so windy day. And if the difference between those two, right, is different from 0, then one of them has a higher wind speed consistently than the other. Right? So this one's a little bit tricky, right? But, or at least to identify. But one kind of dead giveaway is if I give you a table like this, right, where I've got site 2 and site 4, those are the two sites that we're comparing. And then I also give you site 2 minus site 4. That's the difference. Right? I'm giving you the mean of the difference and the standard deviation of the difference. So this here is the difference. If I'm giving you the mean and the standard deviation of the differences, you know it has to be matched pairs. So this makes it paired data. What's nice about paired data is on your formula sheet, right, you've got null hypothesis at mu diff, or we did mu d because I got lazy in class, right? But you can use diff or d, doesn't matter. As long as you use one of those, because you have to indicate that you know that you're analyzing the differences. The null hypothesis will always be mu diff equal to 0, right? Once you've decided you have matched pairs, this is the null hypothesis. And then here, so for our alternative hypothesis, we have to figure out, okay, what's the sign in the alternative hypothesis? It's a little bit tricky because here we want to know, is there evidence that either of these sites has a higher average wind speed? Because I'm not saying which site has to be higher, right? I just want to know, is one higher? That's the same as saying, well, are they different? Right? If they're significantly different from each other, that implies that one has a higher wind speed. So it's a two-sided test because you've got the not equal to in your alternative hypothesis. Calculate your t, right? X bar of the differences minus the mu of the differences. Mu diff is always 0. So it's always going to be X bar of the difference is minus 0, and then calculate your t, you get 2.669. With a t that large, we already suspect that we're going to reject the null hypothesis, but we have to find the p-value just to make sure. So again, showing off that you know how to find the degrees of freedom, so using the t-table with degrees of freedom of 11113, you go to the table and you're left choosing between 100, 1,000, and infinity. Z star is infinity. So you have to round down to 1,000. You're going to find that your calculated t is between 2.581 and 2.813, which means your two-sided p-value, right? If you go to the very last row, that's your two-sided p-value. It's somewhere between 0.005 and 0.01. Right? So really small p-value. Our conclusion then, since our two-sided p-value is between 0.005 and 0.01, it's less than our assumed alpha level of 0.05. Fair enough. This means we have enough evidence to reject H0 in favor of HA. All we can really say, because we did a two-sided test, is that therefore there is evidence that one of these sites has a higher average wind speed. If you have a look at the actual data, right, site 2 had a higher average wind speed than site 2 or site 4. And so just looking at those, we would say we suspect that that one's the higher one, right? Just because that's what the data is telling us. Okay, but As far as our actual conclusions that we are allowed to draw, is that just one of them has a higher average wind speed. Any questions about that one? Construct a 99% confidence interval for the mean difference in wind speeds. Should be a line break here, but using the T table, so again, we need a confidence level of 99%. So you have to find your degrees of freedom, 99% confidence level to find your T star. We find 2.581. Empty formula, plug in the values, show me your margin of error. This one's optional. And then show me your rounded ones. Okay. Interpret the interval. We're 99% confident that the interval from 0.007, so not very big, right, to 0.401, which seems to be pretty big, captures the true mean difference in wind speeds. Again, because 0 is outside this interval, that coincides with rejecting the null hypothesis in favor of the alternative. But that's not part of the question, so I don't have it on. Okay? But you can start thinking about it that way. Let's get through the last one. Any questions though? No. A factory hiring people to work on an assembly line gives job applicants a test of manual agility. This test counts how many strangely shaped pegs the applicant can fit into the matching holes in a 1-minute period. Sounds fun. Well, not under pressure, but so I guess what's the point? The table below summarizes the data by gender of the job applicant. We've got 50 males, 50 females. We've got the means of both groups, and we've got the standard deviations of both groups, right? So because you have all this information, right, sample 1, sample 2, there's no way to match the two. Also, I haven't given you the mean and the standard deviation of any differences, so that's how you know it's going to be just 2 sample means that you're comparing, right? 2 independent sample means. I'll throw in the word independent here. Independent. I'll type a righto. Is there evidence of a difference in the average number of pegs that makes that males and females each can place? Remember the one thing that we said for the null and alternative hypothesis, right? The null hypothesis on your formula sheet is that mu1 equals mu2, but for full marks, you have to use question-specific subscripts, right? Just to show me, to make it easier for me to read your alternative hypothesis, right? Does your alternative hypothesis make sense? So must use question-specific subscripts in H0 and HA. So here, this is a 2-sided test because we want to know if there's a difference between the 2 groups. So mu m is equal to mu f, or they're not equal to each other. Doing the test, it's a little bit more work, right? But if you just kind of take your time and go through it properly, right? Make sure that you show your empty formula, plug in all your values, and then just make sure that you square your standard deviations before you divide by n. You should get a t of 2.478. Once you have a t, though, you're back into the t table and it works the exact same way. The only hiccup is that now, because we have these 2 sample sizes, we have to use the smallest sample size minus 1 as our degrees of freedom. Okay. And your degrees of freedom are all on the formula sheet, right in the bottom corner. So finding the p-value, our 2-sided p-value looks like this, right? So using the t-table with degrees of freedom equal to the minimum of n1 minus 1 and n2 minus 1 is a minimum of 49 or 49, which is just 49. Again, we've got that dilemma, 40 or 50, we have to go to 40, so using 40, we find that t is between 2.423 and 2.704, which means our two-sided p-value is somewhere between 0.01 and 0.02. Since our two-sided p-value is less than our alpha level, 0.05, we have enough evidence to reject H naught in favor of HA. So this means there is evidence of a difference in the average number of pegs that males and females each can place. Okay. I'll blab through the confidence interval quickly here. Find a 95% confidence interval for the difference in the mean number of pegs that could be placed by men and women. What's nice about this one is really if you start here and you just go straight to saying, okay, well, this whole bit equals 0.597369236 from A. You don't have to calculate it again. You can just give me the empty formula and then go straight to here, which makes this optional and this optional. And you even know this one as, oh, what was it? 1.48, sorry, I have it right there, from A. As long as you tell me where you're pulling these values from, you've already shown me all that work, so you can just recycle it. And again, plug in the values, show me the margin of error, and then you can go straight to the rounded answer. This is optional. So we're 99% confident that the interval from 0.16 to 2.8 captures a true difference in the mean number of pegs that could be placed by men and by women. Good. Any questions? Yeah.
In terms of putting the female or the male
Yeah.
in front, when you subtract each other, which one you determine goes first?
It doesn't matter the order, as long as you're consistent, right? In treating this as group 1 and this is group 2, it doesn't matter. Yeah. Any other questions? So again, I'll be here if you have any questions, and otherwise I'll see you on Monday. Sure.